Hello ladies and gentlemen, thank you for tuning in again today to GGS 300 Quantitative Methods for Geographical Analysis. This is the fifth lecture. Today we're going to be covering probability. So just a quick update on the current work. The fourth homework assignment is going to be set this week. The discussion boards are now up and the tests are also now up. So all of this work is going to be due on the 1st of October. So please do make sure that you're engaging with the content and keeping up with the work, and let me know if you have any particular questions or queries, and I'll be happy to help you. So in this class today we're going to be focusing on probability. It's an introduction to probability. I remember that some of you have covered some of this material before from the baseline survey that I set at the very start of term. So that's good. I'm not sure if you've all covered it in quite the depth that we're going to go into today, as we're going to be covering distributions, z-scores, and going into some more complex aspects of probability. So let's begin with basic probability and some definitions. So exactly what is probability? Well, this is the chance or the likelihood of a particular outcome actually occurring. And there's various different types of processes which we might be interested in measuring. So we're going to cover deterministic processes, random processes, and stochastic processes. I'm going to start here focusing on deterministic processes, which actually in the spatial sciences we don't have that many realistic examples of. So a deterministic process essentially is the type of phenomenon that can be described and predicted with certainty. So essentially there's no element of randomness within it, and therefore we should be able to exactly predict the future state of a process or a system. This is quite common within experimental science, for example. So if we were to create an experiment where we were able to control for those other factors which might introduce noise or randomness into our results, then we would be able to measure physical properties, for example, of a system in quite a specific way. So I've just given you some examples here of deterministic processes. So particularly in terms of Newtonian physics, the movement of objects and planets, and that could yield the number of daylight or nighttime hours, for example. And also in terms of Maxwell's equations, so the behavior of waves, and that's light, radio, ultrasound. And I just gave you that example before of how we could predict a deterministic process, possibly in experimental conditions. And if we were interested, for example, as we show here, in measuring sound, sound waves or cell phone signal, if we had controlled conditions, maybe a 500-meter indoor space, and we wanted to measure what the sound would be between two different points, and then we'll be able to measure that in quite a fairly controlled and predictable way. That is because we've got mathematical models to understand this. But also it's partly because it's very controlled, all the conditions in that particular context, so it's quite detached from reality. When we actually get into spatial science and we're measuring, particularly where humans are involved and social behaviours change, it's very hard to predict potential outcomes. Prediction's a very tricky thing to do. Okay, so that's one particular type of process, one that's predictable with no randomness. And then we move on to probabilistic processes, and the clue for why this is relevant to this particular class is in the title here. So within spatial sciences, we define a probabilistic process as any spatial phenomena that can be described and predicted using likelihood with some sort of degree of uncertainty. So just imagine that we have some expectation about how likely an event is, and then we have some randomness and noise, and that may lead to some sort of probabilistic outcome where it could fall into two different camps, as I describe here. So it could be a fully random process, or it could be a stochastic process, and I'm going to give you a bit more information as to what those two are. So a fully random process is like those processes which we covered in some of our previous classes, such as descriptive statistics. So if I was rolling a die or tossing a coin, there would be the same probability based on all of the outcomes, whether it's a head or a tails, or whether it's a 1, 2, 3, 4, 5, or a 6 if I was rolling a die. There are few examples of this type of random process in the spatial sciences. What's very, very frequent and what's very, very likely within geographical sciences is stochastic processes. So these are those types of processes where the outcomes, the likelihood outcomes are specified, and they're not all equal in terms of how likely certain outcomes are. So for example, we could think of different weather phenomena as being stochastic processes. A hurricane, or potentially also, I think a hurricane is probably quite a good example. We have a semi-random element within the trajectory of a hurricane, which affects where that weather pattern is going to go. And that's one reason why, if you watch the Weather Channel, for example, they'll make an estimate for where they think the path of the hurricane is going to go. And the way that they get that path is actually by using hundreds or thousands, almost millions of runs of each models, and they average across all of the paths so that they get some sort of mean trajectory for where they think it's going to go. And this process, I've called it model ensembles here, but you can think of it as a Monte Carlo simulation. So that's where, rather than running an experiment once, you might run that experiment 10,000 times, and you get convergence towards a set of particular outcomes. And that's very useful, because if you're not able to do a direct prediction of an outcome, perhaps because it's stochastic, producing one prediction might have a lot of uncertainty attached to it. By using this type of approach, you're able to then quantify the level of uncertainty in the estimate, but also provide a mean that captures some of that variance, and therefore hopefully provides you with a better estimate overall. So anyway, I've just categorized stochastic processes within this kind of within this diverging space of deterministic processes at one end, which have no randomness, and then random processes at the end, which at the other end, which have uniform outcomes and lots of randomness. And then in the middle, what we end up with essentially is a set of stochastic processes, which are very frequent in our everyday lives. So we've discussed probability, we've defined what that is, but what does that mean, mathematically? Well, the probability of A denotes the probability that outcome A might actually occur. So how do we define what PA is? Well, we take the frequency, so the absolute frequency of a particular outcome A, and then we divide it by the frequency of all other outcomes, okay? And that's going to give us a value that's between 0, so definitely not going to occur, or 1, where we're certain that this outcome is going to occur. And this is going to be fairly central to how we understand probabilities as we move through this course. So just to give you an example, if we go back to one of the most simple probability-based experiments that we can carry out, we can have a single die, and the question would be, well, what's the probability of rolling a 6 from that one die? And therefore, we would say that there are 6 potential outcomes. So to get a 6, that would just be a single outcome. So that's 1. So that's the numerator up here, FA. And then we'd be interested in, well, what's the frequency of all of the outcomes? And obviously there's 6 potential different outcomes. So we would then divide it by that number. So we get 1 over 6, which when we carry out that calculation, we get 0.167, which is approximately 16.7% likelihood of occurring. So for every time that you roll a dice, the likelihood of you getting one number out of all of those potential options is about 16.7%. Okay, so that's highly stylized, and it might not be the type of thing that we we usually address within spatial sciences. I think rolling a dice is just that standard example that people will use when you get taught probability, because it's simple for people to understand. Let's take a geographical example now. So let's think about precipitation and the number of wet or dry days that we might have. So let's say that we have 100 days, we have 38 wet days and 62 dry days. For us to calculate what the probability is of a wet day, then that's PW, and we would have to calculate, we would have to divide the number of wet days that we have over the time period by the total number of days in the time period. So that's 38 over 100, which gives you 0.38, which therefore is 38% probability of there being a wet day. So exactly what is the relative frequency? Well, I define it here as the ratio between the absolute frequency, so that's the raw value, and the frequency of all outcomes. So the absolute value is the actual number of times that something has occurred. So that could be 38 wet days. And then the relative frequency relates the frequency of that one outcome to the overall number of events. And all relative frequencies add up to 1. So the absolute frequency of wet days is 38, but the relative frequency compared to all of the days is 0.38 or 38%. Okay. So just moving on, staying on this concept of relative frequency, the size of the experiment has a really large impact on how you calculate the relative frequency, and that's particularly because if you have processes which have a large stochastic or random element, then just small sample sizes are going to have very large amounts of variance within them. So just to give you one example, if we tossed a coin and we looked at which way up it was going to land, it would be impossible to predict the outcome. So we wouldn't know whether it's going to be heads or tails with certainty. But if we toss the coin repeatedly again and again and again, the actual proportion of the outcomes, either heads or tails, will tend towards, converge towards a particular relative frequency, which is obviously for tails and heads, it's going to be 0.5, so 50% frequency, 50% likelihood. So there is a 50% chance that it will be one of these two outcomes, but the number of times that you run the experiment to get to that number actually has a large impact. So for example, if I just show you here in the table, maybe if we do 10 coin tosses, we might get 8 different heads values, and that means that the relative frequency would be 0.8. Actually, if we then roll that forward each time, so we keep going up to 100 coin tosses, or 1,000, 5,000, 10,000, 15,000, 20,000, you'll see that the relative frequency each time starts to converge closer and closer onto a single value, which is around 0.5. And this is really important, particularly if you're sampling, or particularly if you're modeling a stochastic system using probabilities. You need to make sure you have enough iterations to ensure that you're getting towards stable converged values. So this is an important principle which has just been broken down here in quite a simple way. We do have terms and definitions which we might just need to cover. So an experiment is a particular activity that gives rise to a set of data. The sample space is the set of all possible outcomes that could be selected from a particular experiment. An elementary event is basically an element within that sample space, so something that could possibly occur. The trial is an action in an experiment. You may also hear me refer to this as the number of permutations or the number of iterations upon which we run a loop or a model or an experiment. This is, it's a repetitive activity. It's not just something that we do once, and each one of those iterations is called a trial, essentially. And then finally, we have the outcome, and that's one or more elementary events of an experiment. So let me just give you some examples there of those definitions, just to cement your thinking. So in terms of the probability of getting at least 1/6 when rolling a die twice, the sample space is quite large. It's going to be every single possible combination that those numbers could be. The elementary events are all of those events which fit are essentially the aim for the experiment, the hypothesis that we have. So that's any event here that contains a 6. They're all elementary events that meet the criteria we specify. The trials, well, essentially we're saying that we're going to roll the die twice, so we have 2 iterations here. And the outcome is that we've rolled the die and it's produced a set of numbers. Neither of them are 6s. That's an outcome that we obtain. Okay, so that can go into the distribution of outcomes that then we measure at the end to understand something about this process. And it could be the same if we were interested in the probability of there being more than 60 inches of annual precipitation. The sample space would be any continuous number, so it's therefore above 0 or equal to 0. The elementary events that we're interested in here are those events which exceed 60 inches of precipitation. And the trial is the recorded precipitation for a year, so you could record that daily and then essentially add up all of those values to get your annual amount. And the outcome could be 63.5. So rules of probability. So we went through this before, that your probability value is going to be between 0 and 1. So 0 is you're certain that it's not going to occur at all, this particular outcome, or 1 is that you are absolutely certain that that one outcome is going to occur. So the complement of an outcome is essentially that if we have an expectation, the probability for a particular event, say the flooding of a river, say we think that that's going to happen, there's a 40% chance of the river flooding in a particular year, then the complement of that outcome is the chance of that not happening. So if it's 40% for the river to flood, then it's 60% for the river not to flood. And those two probabilities add together in order to get that total number of values, which is 1 essentially. And then there's 3 different types of events that we may want to categorize, which can affect our probability estimates. And here they are statistically independent events, mutually exclusive events, or non-mutually exclusive events, and they have different ramifications for how we approach these particular issues, and particularly how we quantify the probability within this particular method. So statistically independent events, this is where one event does not influence another event, and I'm going to keep coming back to this as a really important part of probability. And it's going to be really prominent in what we do later in the course, because many of those more advanced statistical techniques that we use have this assumption of statistical independence within them. So if I flip a coin and I get a heads, and then I flip a coin again, the second toss is not influenced by the first toss of the coin that I carried out. Okay, and this is really important. So if we want to calculate the probability of 2 statistically independent events, we need to firstly ensure that they are independent, and if they are, then we can use the multiplication rule. Okay, so the probability of A and B occurring together is essentially the probability of A multiplied by the probability of B. So, okay, what is the chance of, so what's the probability of flipping a heads and then a tails in order? Now let's think about that. So the probability of those 2 events in that order is the probability of heads, which is obviously 50%, 0.5, multiplied by the probability of tails, which again is also 50%, so 0.5. So when you multiply 0.5 by 0.5, you end up getting 0.25, or as I've characterized it here, 25%. So out of those 2 coin tosses, there's a 25% chance that you might end up with the heads and then the tails. I think that probability is one of those hardest areas for you to kind of grasp. It takes quite a bit of time. There are going to be quite a few equations that I end up having to show in this, and therefore I'm keen to try and lean on some more graphical aspects to try and emphasize how these calculations take place. So just to give you an example, let's rerun that calculation, but let's use a diagram, which basically provides graphically the different options and outcomes for each one of those very simple routines. Okay, so we're just flipping a coin. There's only two potential outcomes. So we start here, and we've got 50% chance of flipping either a heads or a tails. Okay. And if we did flip heads first time, then we would flip again, and therefore we would have either a 50% chance again of those two outcomes. And we can see now that for us to get down here, we would have to flip the first time heads, which is 0.5, and the second time a tails, which is 0.5 for the second time. But obviously, those need to happen sequentially. And that's how we get the 0.25% outcome. You can see that by the time we get down here, actually, that there's 4 different potential outcomes, and that's mirrored in the fact that we have this 25% share. These types of diagrams for different probabilistic events are used really commonly. So, for example, we've used them in insurance before. So what's the probability of a ship crashing in a major shipping lane? And that would give you some estimates, maybe it's 0.0001% based on the number of ships that go through a very busy shipping lane. And then there's another probability for, okay, what happens if there's then a fire on that ship, and there's all those different outcomes. Okay, does one of them sink? Does one of them burst into flames? Do both of them survive? And therefore you can put probabilities on all of these different potential outcomes. So you get an event tree. So that's essentially what this is called. I like to see things graphically and visually. So that's why I'm introducing this concept now, because it's easier to kind of map out and understand exactly what's happening at each one of these stages. For those of you maybe who aren't as comfortable just getting the pure math first time. Great. So let's move on now. Let's cover mutually exclusive events. So this is where there's absolutely no overlap between the different events. So the events can't appear at the same time. So what happens if we want to calculate the probability for these events? Well, essentially for A or B, we need to add together these two probabilities. So when we use OR, this basically means that the pick is successful if we meet either of the two conditions, essentially. So here I've just chosen a very simple example. I'm a crazy dog guy, so I've picked more dogs. So here we have the dog breeds and the quantities of dogs. So there's 10 different dogs, there's 4 Labradors, there's 2 German Shepherds, 2 Golden Retrievers, 1 Bulldog, and 1 Poodle. So my question to you is, what's the probability of picking either a Labrador or a Golden Retriever? Now, these are mutually exclusive events. You can't simultaneously be both a Labrador and a Golden Retriever at the same time. These are completely different breeds. So what's the probability of actually getting that? Well, first we need to estimate what the probability of picking a Lab is. And obviously there's 4 here, so that's 4 out of 10. It's a 40% chance. And then we need to calculate, well, what's the probability of getting the Golden Retriever? So there's 2 of them here, so that's a 20% chance. So when we add these together, we get a 60% chance that we're either going to pick a Labrador or a Golden Retriever. Okay, so I hope that that's clear. If it's not, skip it back, rewatch this part of the video. Hopefully it'll be clear. My purpose here is to pick very simple examples, and that's why I like to pick those where you may have only a certain number of elements which add up to say 10, because it's a nice decimal to start to understand the different probabilities with. Factors of 10 are nice. Okay, so let's get on to the final type of probability rule here, and that's where you could actually have overlap between the different groupings within your rule set, for example. So here I've said, well, what's the probability of picking a Labrador or a black dog? And the issue, of course, is that you could have both a Labrador, which is also black, and that's why when you need to calculate the probability, you can't just sum the two probabilities together. You also need to take into account that you could have some overlap. So if we're interested in P or B where there is overlap, then we would have to add the probability of A to the probability of B, and we need to subtract the probability of something occurring that could be both A and B. Okay, so for it to be lab or black, then we would need the probabilities for these relevant criteria. So the probability of it being a Labrador is 4 because we have 2 black Labradors and 2 yellow Labradors. So that's a 40% probability. What's the probability of it being black, that one dog that I pick? Well, we have 2 black Labradors and we have 1 black poodle, so that the chance, therefore, is 30%. But then we also need to take into account those non-mutually exclusive events, which include, black Labradors, for which we have 2, so it's 20%. So we basically need to add together a 4 out of 10 and 3 out of 10, which is 7 out of 10, and then subtract those non-mutually exclusive events, which are 2 out of 10, so 20%. And what we end up with is 7 minus 2, so we get 5 out of 10, which is 50% chance of either picking a Labrador or a black dog. Okay, so I hope that is relatively clear. If it's not, then take some time to rewatch the video again, and hopefully you'll be able to be clear about those 3 different types of events for calculating probabilities and the rules included within them. So what's a probability distribution? Before we progress, it's important just to touch on this. So the probability of an outcome follows consistent patterns. So if you know the shape of that pattern, then you can use it to do different things. You can use it where maybe you don't have actual data for a variable, or maybe you don't want to collect all of the data for a variable. Maybe you want to carry out an experiment for where you don't have a complete data set that you want to test. And essentially that pattern here is the probability distribution. And it's got a specific shape, and that specific shape is very useful to us. So I define here a probability distribution as being a table, a graph, or a mathematical function that describes the potential value of a random variable and their corresponding probabilities. And what's important is that the probability distribution, which sounds really scary, is actually very similar to work that we've already done. It's very similar to the frequency distribution. So you'll remember in the frequency distribution, the y-axis shows the number of occurrences that we have. So in the first, second, third lectures, we were focusing on frequency distributions. And then now what I want to do is to think about what would happen if we change the y-axis of that frequency distribution, but we actually now said that it's the probability of occurrence. So if you've measured a set of outcomes and it has a particular shape, you can actually think of these as not just in the empirical frequencies that you've got, but you can think of these as the probability that one of those bins that we measured it will be the value that we next pull from the distribution will be one of those bins. Okay, so let me explain this in a little bit more detail for you. You will remember this example from the previous lectures. Within there, we had the hypothetical experiment where we had 2 die, and we were rolling those 2 die, and we were basically getting the mean value from all of those trials or iterations, whatever you want to call them. And empirically, if we carried out that experiment, we would end up with this normal distribution shape. Okay, so the mean value on average as you repeat the experiment will be close to 7. Okay, we'd be very unlikely to get mean values out here at the edges. The point is that once we have this shape, we could then turn this into a future likelihood. So we could say if we rolled the dice n number of times, then we would expect that the mean of the data set would be like this. Or we could use that shape of that distribution to put a probability on the chance of the next value being pulled out of that distribution as being x. And that's really useful. So within this lecture now, we're going to cover a variety of different types of probability distributions, and we're going to cover some examples where we could apply this thinking to real world problems, hopefully make the world a better place. So there's two major types of probability distributions. Firstly, we have discrete distributions. So that's where outcomes occur which could be integer values. They could just take a set of a very small number of outcomes, so they could be binomial or Poisson, as we'll cover within this lecture. So that could be nominal or ordinal data. And then you could have, on the other hand, continuous outcomes which are infinite. And then later in this class, we will pick up on the normal distribution, which I'm pretty sure most of you probably have already heard. You probably heard me mention it a few times within this particular class already in the earlier lectures. Okay, so let's start with the binomial distribution, which is a discrete probability distribution which has only two outcomes. And the hint is in the name. Bi, as in bicycle, two wheels, binoculars, two optics. Here we have binomial, so it's two potential outcomes which are discrete. Binomial distributions deal with trials that consist of either or outcomes as a consequence. So a person either has a job or they don't, and a river is either above or below a specified flood level. Or respondents in a particular poll may either favour or oppose a particular issue on a binary scale, for example. So just imagine that we have sequences of outcomes which can only take these two values: yes, no, true, false, success or fail, 1 or 0. There are some requirements for the binomial distribution, however. So it would arise when we have repeated trials, each of which results in one of two outcomes, as I've already mentioned. Importantly, though, the probability of one of those outcomes needs to be constant for all the trials and is denoted by the letter P. So this is important. And then the complement of that probability of the other outcome is denoted by Q. So we can obtain Q basically by subtracting P from 1, and that gets us the complement probability. Importantly, as I've already mentioned, the trials must be independent, and the number of trials is denoted in this instance by the numeral n. The outcome then follows a binomial distribution based on these parameters of P and n. So for a binomial distribution, the probability of a given outcome occurring x times in n trials is as follows. And I know that this looks like a scary equation, but please just bear with me while I explain it. I'm going to give you both the math version here, theoretically, and then I'm going to give you an example, and I'm going to give you some Excel code, and then we're going to go later on in the lab, and we're going to look at how we generate this within R. So I don't want you to get too intimidated by this work, but just accept that we're going to go through it in a variety of different ways, and hopefully you will be able to get your head around this concept using one of those particular approaches that I will use to demonstrate the use of this particular concept. So as I already stated, n is the number of trials, as we see here. P is the probability of the given outcome, Q is the probability of the complement probability. X is the number of times the given outcome occurs, and n is the factorial. So when you see the exclamation mark, the factorial counts the total number of possible permutations. So if the factorial is 5, then basically what that means is that we multiply 5 by 4 by 3 by 2 by 1, we get 120. They're the total number of potential outcome combinations that we could have. Okay, so for the probability of a particular outcome, we multiply the number of trials, so the factorial of the number of trials, and then we multiply it by the probability to the power of x, so the given number of times the outcome may occur, multiplied by q, which is the complementary probability, to the power of the number of trials minus the number of times the outcome has been given. And then so that's the numerator, and then we have to get the denominator, which is the factorial of the number of times the outcome is given, and then multiplied by n minus the number of times the. So we're going to calculate this now so that we can understand exactly what's going on. So let me give you an example. A potential vegetable grower is seeking to start a business in a new location, and that person wants to go out and buy the land, and then on that land they're able to grow certain vegetables. Site selection is absolutely pertinent to this. So basically, in years where there isn't enough rain, the farmer will essentially have to irrigate the field, and that can be very expensive if there's not water that can be easily extracted, or if they have to take mains water, they're going to have to pay for that. There's an energy cost, there's a carbon cost, and that means that it's going to hit the bottom line of the business growing these potential vegetables, for example. The grower, based on the margins which can be produced for those goods and sold at market, can only afford to actually carry out irrigation on that site for 1 in every 5 years. Okay. One particular site in question, which the grower is looking at purchasing, had enough rain for 21 out of 25 previous years. So the probability of requiring irrigation is 4 over 25, so it's about 16%. So in any one year, there's a 16% chance that that one site may need to use irrigation rather than just natural rainwater. And that's going to cost money. So before the site selection is confirmed and purchased, the question is, well, what's the probability that a grower can meet the requirement for irrigating only 1 in 5, 1 year in 5? So we need to calculate using the binomial distribution. So I've repeated the question just up here. We know that the number of years that we're interested in is 5. We know that the probability of requiring irrigation is 16%, so 0.16. The complement is 0.84. The different potential outcomes is from 0 all the way up to 5, so you could have no irrigation required here, 1 year of irrigation required, 2 years of irrigation required, all the way up to 5 years of irrigation required over those 5 years. And then we have the factorial value, which is for 5, when you multiply all those values together, you get 120. So these are the input values, and we have the equation over here to the right, okay? So just bear with me here. I thought that rather than just theoretically explaining it here and then just dumping the code on you with R, I would actually just tap these calculations out in an Excel spreadsheet. And that's because I think that, you know, I write a lot of code, but I use Excel a lot. And I think that particularly for people who don't like the command line, this is a kind of fairly simple and nice way to understand how to do calculations, okay? So what I've done is I've put in the first 4 columns the n value, which is 5, the different x values, and then the probability and the complementary probability for those outcomes. And then I've calculated the numerator and the denominator separately, so you can see what those values are, and then I've calculated the actual probabilities which answer the question essentially. In the final column, px. If you want to run this code, if you want to type this out in your Excel spreadsheet, I would thoroughly advise you to. And actually, what I've done here as a consequence is I've just put down the equations for the numerator and the denominator, so you can just basically tap out these equations. You'll need an equals before it. But essentially, to get the numerator, you would need to take the factorial of a2, which is n here, multiplied by the power of c2 and b2, so that's p to the power of x, multiplied by the power of d2, which has to be q, and then to n minus x. And that should get you the numerator, okay? And then when you carry out the more simple denominator, you just need to type in equals, take the factorial for b2, which is x, and multiply it by the factorial for n minus x, which is the n here, 5, minus b2, which is 0, 1, 2, 3, 4, 5, depending on the row. And then you end up with these probabilities just here. Okay, so please do that. I think it will really help your understanding. And then essentially we end up with these different probability outcomes. So these are the probabilities that you might get outcomes in these particular buckets. So in year 0, that would be no irrigation being required at all. So over those 5 years, there's no years where you need irrigation. You could end up with 1 year where you need irrigation, and you could end up with 2 years where you need irrigation. And these are the probabilities that provide you with some understanding of how to relate it to the previous information which you received. And that's that the grower can only afford irrigation in 1 year of 5. So essentially then we're able to establish exactly how many years are suitable and how many are not. And we can see as a consequence that the first 2 years are suitable. So if the grower can only afford 1 year out of 5, then it's all of those values which fall in these 2 buckets here, which we're interested in. And then all of the other values provide us with that a probability for the number of years where this site would be unsuitable, essentially. And we're able also to graphically display these distributions. So when you see probability curves, essentially that's just a different way for visualizing those probabilities I just showed you. So if I drew a line from here all the way through each of these buckets down to 5, then the area under the curve would provide you with insight as to the probability of each different value occurring based on the value itself on the x-axis and then the likelihood on the y-axis. And that can help you answer the question which we posed. So this is an example from within the book. So I do encourage you to go into the book and read this through, have a look at the calculations again, carry them out. And I think that this is a pretty handy distribution to know. We can also calculate cumulative probabilities. So for example, we might ask, what's the probability of getting more than 7 heads in a row if we flipped a coin for 10 times? So therefore we would need to sum up the probability of us getting 8, 9 or 10 heads, and that's how we would get the P7 value. So just before we finish this section, it's important for me just to identify that there are a variety of binomial distribution functions that are available within R. So binom is the function name, and then for each one of the 4 variants you have a different letter in front. We're going to cover this in more detail in the lab session, but it's important for me just to point this out to you before we progress. Okay, the Poisson distribution. So this is a discrete probability distribution with many outcomes. So the Poisson distribution arises when we have a variety of conditions. This is named after the mathematician Simeon Denis Poisson. So Poisson obviously is fish in French. So he's a very highly regarded mathematician. You'll notice that a lot of the distributions that we cover are actually just named after the people who first hypothesized them. So we've got the Poisson here. The normal distribution is also called the Gaussian distribution after Gauss. And there are lots of other distributions which we won't be covering here, but also have similar names. Okay, so importantly, within the Poisson distribution, the actual event occurrences need to be independent, as I've already emphasized previously. We need to have a fixed interval or time space. The probability of an event occurring within a certain time interval doesn't change. So if we're considering a 10-year period, the probability that event occurs in each year stays static throughout the whole assessment period. And the probability of observing a single event over a small interval is proportional to the size of that interval. So if I have a probability of me getting a phone call in the next hour, if I then extend the time period to 1 day, the probability will be relative to the number of hours within a day, essentially, and that stays constant. And then finally, the probability of 2 events occurring in a small enough interval is negligible. Okay, so Poisson distributions deal with those phenomena that occur randomly across space and time and can be measured in frequencies. They're used quite widely within my area, actually. So anything where you have points occurring in space, and this could be people logging onto a cell tower to access data. You know, every time you want to take a phone call or you log onto Instagram, you're basically transferring data into that point in time. So mathematically, if we want to understand the demand placed geographically onto a cell tower, this is one way that it's commonly done through a Poisson point distribution. So it could also be the number of lightning strikes within a particular area, a quadrat. For example, one of these, it could be a 1 kilometer squared tile. Or it could be, for example, the number of hurricanes that hit Florida in a particular time period, such as a year. So that gives you a bit of a flavour as the types of different applications for Poisson distributions. Now you'll be glad to know that it's actually, I think, a lot easier to calculate the Poisson distribution in comparison to the binomial distribution. And that's because essentially to get the probability of X occurring, essentially what we need to do is multiply the mean frequency of the event, which is lambda, to the power of X. Sorry, not multiply. We need to divide the mean frequency of the event raised to x by the natural logarithm, also raised to the power of the lambda value, multiplied by the factorial of x. So I know again that that's complicated, but actually I think it should be easier. It's fewer calculation steps to carry out than the previous binomial distribution. So what's important, if you're not familiar with logarithms, that the natural logarithm is a mathematical constant, which here we treat as 2.71. So what we need essentially is the input values is the frequency of occurrence that we might be interested in assessing, and we need the mean frequency for that particular event. So the characteristics of Poisson distributions is that they are good for describing rare events, so tail events. And they're not so good for describing things that commonly occur. Ultimately, the distribution is based on discrete outcomes, so you can't have half a tornado or half a hurricane, for example. And we are interested here in the mean frequencies. Again, one of the assumptions is that the occurrences should be random, and technically you could have an infinite number of discrete outcomes. Okay, so let's do an example. So in this example, we're going to be thinking about the number of major hurricanes that hit Florida between 1900 and 2003. So that's a 104-year time span. There were 24 major hurricanes which hit Florida in this period. The number of hits per year as a consequence follows a Poisson distribution. My question, therefore, is what's the probability that Florida will actually be hit by at least 3 major hurricanes in any one year? So that's quite a large number, which means we'll probably end up getting quite a small probability for this event. Don't be fooled by small probabilities. That's one thing that I would say. And just to give you an example, in the Fukushima nuclear power plant accident that took place in 2011 as a result of the giant tsunami that took place in the Pacific Ocean, which unfortunately killed many, many people on the east coast of Japan. The nuclear power station at Fukushima had a tidal wall which was built to withstand a 1 in 10,000 year tidal wave. And unfortunately, the wave that actually hit was much larger than this 1 in 10,000 year wall was built for. So in theory, you think that you can probably neglect small probabilities, but actually they do end up happening. And therefore you do need people in terms of risk to think about these very extreme events. And therefore it's very much a worthwhile topic to think about 3 potential major hurricanes taking place. Okay, so how do we start with this particular question? Well, over here you'll see the Poisson math equation, which helps us calculate this particular problem. What we're interested in is those years where we have 3 or more hurricanes. So basically, we subtract the probability here from 1 of there being less than 3 hurricanes in a year. So as a consequence, we need to subtract from 1 the probability for 0, 1, and 2. Okay, so now we know what we need to do to get the actual answer. Let's do those calculations. So over here, we need to take the mean value, so that the lambda value here, which is 0.23, we need to raise it to the x value for each one of these iterations, so 0, 1, 2, for example. And then we also need to raise the natural logarithm to that mean lambda frequency and multiply it by the factorial for the x value. And essentially what we get is 0.79 for no hurricanes hitting Florida. So basically there's a 79% chance that no hurricanes will hit Florida in any one year based on the time series that we've got here. And then if we calculate this for 1 hurricane hitting Florida, we would get 0.18. So there's about an 18% chance every year that a hurricane might actually hit landfall on Florida. And then for the circumstance where there might be 2 hurricanes hitting Florida in a single year, we'd be looking at about 0.02. So it's about 2%, essentially. Now what we need to do is to add up all of these values, so the 0.79, the 0.18, the 0.02, and we end up with 0.9982917. And that's the summed probabilities for all those years where you have fewer than 3 hurricanes hitting Florida. And that provides us, as a consequence, when we subtract this value from 1, essentially it provides the probability of Florida being hit by at least 3 major hurricanes. And when you look at that in percentage terms, that's each year there is less than 0.17% that there could be 3 major events hitting landfall in Florida, essentially. Okay, so that looks big and scary. I hope that we managed to break that down into the theoretical math equation, the calculations for getting the answer here, the results for each one of the permutations we needed, and then the final calculation with the actual numbers to get the probability required. So if that's still not clear to you, make sure that you rewatch the video and also think about some of those examples that are in the books, or reach out to me if you want further examples so that I can help you get your head around this concept. So you could show graphically the probability for these different hurricanes hitting, and here we have the distribution. Equally, if you were to change the problem and say, well, how many cancelled school days might there be for Mason per year? If you know the mean's 2.4, you would be able to calculate the distribution for that particular problem as well. But I'm not going to go through it in any depth here. So in R, because we will be covering this within the lab, the Poisson distribution has 4 different prefixes, and again, the actual name for calling these prefixes essentially is POIS, so P-O-I-S. That's the R function, and then you have a letter before each one of these, depending on whether you're looking for the density, the cumulative, the quantile, or the random distribution. And they each do different things, and you need to know which one you need to call. But for the moment, I just want to draw attention to these different prefixes, and we'll be covering them within the lab work. Okay, so we're on the home straight now. We're moving on to the normal distribution, which I think is probably an easier distribution for us to understand. It's also the most frequently occurring. So I mentioned before that the normal distribution is also called the Gaussian distribution after Carl Friedrich Gauss, just here. It's the most common distribution. It focuses on continuous outcomes. And if a set of data are actually normally distributed, then the mean, the median, and the mode will all be identical in exactly the same place. The curve is often called the bell-shaped curve, so I think I mentioned this in some of the previous lectures. That's an important term to know. So the mu value here refers to the mean, and the sigma squared value here refers to the variance of the particular distribution. And the total area under the normal curve represents 100% of the different outcomes. Okay. So we could look at different distribution types. So for example, here we have different mean values, 0, 0, 0, minus 2 for this particular pink one here, and then the rest are all centered around the 0 mark. And then for the variance level, the sigma squared value, we have different values here from 0.2, 1, 5, 0.5, depending on the actual shape of the distribution. So here we have one that's quite leptokurtic, here we have one that's quite platykurtic, and this one here looks the most sensible shape. I think there are tests that you are able to use in order to understand whether your data are skewed beyond the normal distribution or not. I'm not going to get into them here. I think it's just important for your future development to know that sometimes you might want to have access to these tests just to make sure that your distribution definitely does conform to this Gaussian profile, this normal profile that we're interested in. So the question is, well, why are we interested in that? Essentially, we can do a variety of different things with the normal distribution. So we're able to understand how much precipitation there may be in different places, what the probability of different precipitation rates is. You might want to understand what happens with different fertility rates by county. And one way that we do this is by using standardized scores. So this essentially means that regardless of what units the data are measured in, whether you're measuring braking distance for a vehicle, which could be in meters, or whether you're interested in measuring the speed of vehicles, you're able to get a standardized score which relates to the distribution of that particular set of data. And this is really powerful. Okay, so this is a concept called Z-scores, and Z-scores essentially are these standardized metrics which are relative to the standard deviation. They're measured in the standard deviation. Okay, so how do we calculate these Z-scores? Well, as I state here, these are the population values to get the Z-score. I think one issue is that we often don't have the population values for us to actually calculate. You know, maybe we sample the population, in which case essentially we would need to use the sample parameters, which I've stated below. So the Z-score for the population is the value of interest minus mu, which is the mean value, divided by the standard deviation. For the sample, we would get the Z-score essentially by subtracting the mean from the observation and dividing it by the standard deviation. It's the same formula, it's just that we use different nomenclature depending on whether you're measuring from the sample or the population. Actually, in the examples that I will give you further on, we're just going to be using the equation for the population. Okay, so what's the relevance of Z-scores? As I mentioned before, these Z-scores are measured in terms of the standard deviation, so the number of standard deviations that each score may be from the mean value. And this is really important because the shape of the normal distribution, as I already mentioned, is stated here. The reason why this is a very useful shape is that then you're able to place a quantified number on the different portions of the data that fall at different places around the mean. So here we can see on the x-axis we have the number of standard deviations. So this is the mean. We have 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean, and vice versa here for negative values. I'm going 1 standard deviation below the mean, 2 standard deviations below the mean, etc., etc. And we can see that 34% of the values lie between the mean and minus 1 standard deviations away from the mean. And the same for 1 standard deviation above the mean, but it also means that then we can quantify how much of the data falls within each portion of the distribution. So this is the proportion that falls above or below almost 2 standard deviations for the mean, so 95%. It's not quite on, but we'll get to that at a later point. And then also we can quantify the portion that falls within 99%. So we can quantify the amount of data that falls within that region which contains 99% of the data. And this is really important when we start to get towards inferential statistics. Okay, so this gives you a little bit of an understanding about the probability of where those values might fall. So how do we actually calculate the Z-score? What's the relevance of it? Why do we use it? These are all valid questions. So can we find a corresponding Z value? How do we find the probability? Well, firstly, I should start by saying that the old way for us to do this was essentially to get a statistics textbook, and in the back it listed all of the probabilities to each Z-score, and you had this very long and manual way to work out which values you needed to grab. It's a lot easier these days. For instance, if you follow the link down here, you actually just have online calculators that help produce the exact number that you might be interested in. That's very easy to calculate. But you can also use computers to help calculate these metrics, which is much better than 100 years ago when people would literally carry it out by hand. Okay, so let's go through one of these worked examples. So if I said to you that a make of car averages 25 miles per gallon and it had a standard deviation of 3 miles per gallon, my question would be, well, what is the probability that I get a car that averages under 21 miles per gallon? Okay. Now that means that we're going to need a set of inputs for this calculation. So we need the absolute value here, and we're interested in the value 21 miles per gallon in order to understand where the other values fall. We're going to need the mu value, which is the population mean. Well, we know that because it said that it was 25 miles per gallon. And then we need the population standard deviation, which we've already been told is 3. So to get the Z-score, essentially when we input those numbers, so we subtract 25 from 21, which gives us -4, and then we divide by 3, which gives us -1.33, okay? And then what we're basically able to do is we're able to follow here. And I've already inputted this particular Z-score. So we found out that the value that we're interested in is -1.33 standard deviations away from the mean. And then what it tells us is for all those values that have a Z-score beneath this amount, the answer is 0.09, which is the answer here, essentially 0.92. Okay, and essentially you have 90% of the data which falls above this value, and then you have about 9% of the data which falls, so it's 91% of the data I said falls, 91% falls above, and 9% falls below, okay? And this is relevant because we want to know what the probability is that the car that you get averages under 21 miles per gallon, and the answer as a consequence is 9%, okay? Right, let's move on. And that's because there are other ways that we may want to calculate these Z-scores, okay? So essentially, what we may say is, well, let's use the same mu, the same mean, and let's use the same sigma value, so the same standard deviation as before. And now let me ask you the question, well, what miles per gallon value represents the 95th percent mark within the distribution of values that you have? So in other words, at what quantile does 95% of the distribution of values fall under this point? Okay, so we want to find out what this absolute raw value is going to be. So we know that we want 0.95 as the probability, when we look up the z-score for this particular level, we get 1.64 standard deviations above the mean. And then essentially when we know the z-score here, we know the population mean, we know the standard deviation. What we don't know is the actual value here. So we need to basically rearrange the equation. And when we do that, we end up with the x value essentially being 29.935. Okay, so how did I calculate that particular value? Well, essentially what we're able to do is you're able to take the population mean here, x bar, for example, and then essentially we're, or mu it could be if you were using the population, sorry. And then what we need to do is we need to add the standard deviation value, which is 3, multiplied by the z-score, which is 1.645. Okay, so here we're taking the 25 value and we're adding 3 times 1.645, and that's how we're able to get this value of 29.935. And that value, as a consequence, tells us that 95% of all of the other values within the data set are beneath this point, essentially. So I appreciate that as we work with these standardized metrics and we start to use a bit more math, this gets a bit scary and starts to get a bit intimidating. But what's really nice about these standardized scores is then you have a quantified way to understand different data sets in a common mathematical framework, and it's really powerful, and we will be progressing with these techniques that we've developed within this class as we move towards using more inferential based statistics, when many of these kind of basic assumptions about, for example, independence between draws of the sample will be really important. So the standard normal distribution is also called within R using norm, and then it has a letter before each one of these function names to indicate whether it's density you're calling, cumulative or quantile or random distribution. Okay, so we will cover this within the lab. I don't really want to get too bogged down with it here. I just want to point to you that this is where we're going. Okay, so we are then able to convert these probabilities into maps across space, which is important given the fact that we're spatial scientists. So previously we just focused specifically on the probabilities in a particular place. Maybe it was a single site, maybe it was GMU campus, maybe it was a river or a state. But you can transfer these probabilities into different maps. And actually this is really big business. You know, a lot of those companies, if you take risk management solutions, for example, which has its head office in Silicon Valley, but it also has a huge office in New York, actually on the Jersey side of the river, of the Hudson, has a big office in London as well, also in Japan. I mean, they are charging millions of dollars per year to insurance clients in order for them to access their risk maps, which relate the probability of different hurricanes or earthquakes having an effect on buildings in different locations, okay? So, you know, you pay for your building insurance every year, and your insurer needs to care about how likely your building is to be, you know, badly affected by a flood or a hurricane or an earthquake, because they're going to have to pay out the cost of the building if a bad event happens. So they need to be able to get some understanding spatially of the risk in order for them to be able to price the premium for your insurance product that you pay on your house or your family pays, for example. Okay, so there are some requirements for these probability maps. So here I've just emphasized that they need to essentially be continuously distributed across space. And often, you know, these probability maps can be for natural or physical phenomena that take place in different places. So I've given you the example of natural hazards, whatever they are, whether it's flooding or earthquake or hurricane. I've also just put down an example here from a paper which I was reading, which came out yesterday, which is actually a radio map. So this is a space, you've got the y coordinate and the x coordinate. And essentially, this is the probability of your signal phone, your cell phone signal dropping below a working threshold. And actually these green parts here are roads where you're in the open space. And then the red parts here are different building areas where, essentially maybe you're in the middle of a building complex and you've got multiple layers of steel and concrete between you and the cell tower, which is on the top of the building. And that phone signal may not be able to travel through, and therefore, this is a stochastic process, and therefore we can provide a probability that this may or may not happen. You can think of these probability maps essentially as heat maps. So 1 up here is with certainty it won't work, and 0 down here is with certainty it will work. And generally, cell phone signal is much better when you're outside because it doesn't have to penetrate through the building. Okay, so that's just one example which I gave you. Isoline maps are another example where you could have the probability of peak ground acceleration as a result of an earthquake. So this is showing you those seismic areas within the states. So not a vast amount of activity around the Gulf, for example, but particularly across the fault that runs down through California on the west coast, then there's a significant chance of there being quite a large event from an earthquake because you're so proximate. And therefore, as a consequence, your building insurance premium in these areas, particularly around the red, because there's a much higher probability of this exceedance threshold being passed, would be much higher. And you can also, you can develop these maps and relate the spatial dimension to portions of your data that you might be interested in within the distribution, okay? And if you're doing risk modeling, like I've done a bit of risk modeling, I've published a few papers on that, you're basically always going to be interested in long tail events. So those events which go far out to the extremes and therefore where you need to have some sort of quantified understanding of how frequent they may be. And the benefit here is that you can specifically hone in on those parts of the distribution, and then maybe you're able to just map those specific areas where you think they could be most at risk from these particular events. So that's quite nice. You can go from the 2D perspective into the 3D, graphical perspective here into a spatial 2D, 3D or 4D model. Okay. So this is me now drawing to a close this whole unit of the course. The midterm exam will cover this first unit when that's set, and I'll give you information about the midterm in due course. Please let me know if you have any questions or queries that you want to follow up on. I'd love to hear from you. It'd be great to engage with you. I'm just sad that we're not able to actually sit down and have a good discussion about this content. And you can really, in that environment, we can really engage with each other. It's a lot harder async. But do please reach out to me. I've definitely tried to engage with you guys where I've seen there to be a need. And if we've not had a chance to speak yet, then it would be great to hear from you. Okay, so I'm going to draw this to a close now. This was the 5th lecture on probability. There will be a lab that follows up to it and an assignment, so it'd be great if you could watch those following videos and then make sure that you get the outstanding work that I mentioned earlier on within the lecture handed in on time, please. Okay, fantastic. Thank you for tuning in today, and I'll see you all soon. Goodbye.